Hi, welcome to this lesson on trigonometry, trig identities part 2. Let's have a look at question 5. So I see a left-hand side and right-hand side that both have fractions. So immediately I'm going to think of restrictions that could apply here. So I would say for the left-hand side, in terms of restrictions, the denominator cos x plus sine x, or cubed, so essentially I'm just looking at this part here, when that's equal to 0, then we have division by 0, okay, and that'll be undefined. So if I solve this trigonometric equation, find the x values in this given domain, then those will be the x values that are restricted from this identity. Okay, so what I'm going to do is I'm going to move over cos x to the right hand side, so it becomes negative cos x. Then I'll divide both sides by cos x, so I'll get sine x over cos x, which is tan x. And then negative cos x divided by cos x is just negative 1. So I can solve this trigonometric equation, so I've got my cast diagram up. Okay, so therefore my reference angle is going to be tan inverse of positive 1, which is 45 degrees. So tan is negative in the second and the fourth quadrants. Okay, so therefore I could say x equals, so in the second quadrant is 180 minus the reference, which is 135 degrees plus k times 180. And for tan, usually you solve one of these, but if you solve both, one of them usually encapsulates the other one. So what I mean by this is that or x can equal 360 minus the reference, which is 315 degrees, plus k times 180. And you can see you can get all these solutions from this one here. Because if you just add 180 to this number, you get 315 and so on. So generally when it comes to tan, you just need the one solution. With sine and cos, you need both. Okay, so if I put k equals 0, I'm going to get 135 degrees, which is inside that given domain. If I put k equals 2, then we'll be outside here. So anything greater than 2 won't work. And if I put negative values for k, I'm going to get negative values for x, and that's outside the domain. So that's the only applicable value here. Same thing here, if I put k equals 0, or sorry, if I put k equals 1 here, I would have got 315 degrees. Okay, but the goal there, what I wanted to show is that if you looked at this equation as well, if you put k equals 0 here, you're still going to get 315 degrees. So the solution comes out anyway in the first set. Okay, those will be the only applicable solutions inside that given domain for the left-hand side. So the restrictions, so for the left-hand side, it's going to be x cannot equal 135 degrees and x cannot equal 315 degrees. Okay, that also works for the right-hand side because if you put those values in, you should also get undefined values. And we can see that for the right-hand side, the denominator is 1 plus sine 2x. So when that's equal to 0, that'll give us the restrictions. So if we solve sine 2x equals negative 1, that's a trigonometric equation we can solve. And again, in your cast diagram, where is sine negative? The third and the fourth quadrants. Okay, so the reference angle is going to be sine inverse of positive 1, which is going to be 90 degrees. So therefore, the angle here, 2x, must either equal 90 degrees plus k times 360, okay, or the angle 2x must equal 360 minus 90, which is 270. Sorry, so for this one here, let's just go back to this first one. Okay, the reference angle is 90 degrees. So in the third quadrant, it's 180 plus the reference angle. So the 2x is equal to 180 plus the reference. So that's 180 plus 90 is 270 degrees plus k times 360. Or the angle 2x is going to be 360 minus the reference angle, which is 90. 360 minus 90 is 270 degrees. Okay, you can see you get the same solution set in both cases. So you just need to solve for one of them. Okay, so if I divide both sides by 2 here, I get x equals 135 degrees plus k times 180 degrees. Now, where does that look familiar? That's exactly this one here. So it's going to have exactly the same undefined solutions. Okay, so that is the restrictions. So let's make some space now and then prove the identity is true. Okay, so I'm going to start, I think, maybe with the both sides look quite complicated. But I think I'm going to go with the left-hand side. So let's see what happens. Left-hand side. So here's my proof. that's going to equal cos 2x all over cos x plus sine x all cubed. Now, when you see a question like this and there's a cube or power 4 or power 5 or whatever, they're deliberately doing this so that testing, can you maybe see if something simplifies on the top or bottom that could cancel those powers out somehow? Because trying to expand those powers is quite messy and lengthy algebraically. It's not impossible, but it just requires a lot more effort, and things can go wrong if we miss a step or do something wrong arithmetically. Okay, so what I'm going to do is I'm going to think, this cos x plus sine x, maybe if I can get cos 2x to maybe have a factor of one of those, then it'll hopefully simplify. So if I think of cos 2x, which trig identity am I going to use? So the double angle, there are 3 variations, and I think I'm going to use the cos squared x minus the sine squared x one. The reason for that is that this is the difference of 2 squares, which will have a cos x plus sine x factor. So that's my motivation for going for something like that. Okay, so on the top now, difference of 2 squares, so that's cos x minus sine x times cos x plus sine x. So you can see your algebraic toolkit needs to be here, difference of 2 squares, and then this is cos x plus sine x all cubed. Now there's a term here with a given power of 1, and there's a term here with a given power of 3. So this entire term divides out once, and that becomes a square power. So it's equal to cos x minus sine x all over cos x plus sine x all squared. Now, I know I'm on the right path because look at this motivation. The right-hand side has a cos x minus sine x. So that was even more motivation to choose cos 2x as this variation of its identity. Okay, so the right-hand side can give you clues. Always look on both sides and see which identity should I probably use to make it look like the other side. Okay, so we're almost there. We've got the same numerator now for both sides. But now if I square out this, okay, so it means I'm multiplying it by itself twice. So cos x times cos x, so I'm just going to note that over here. So that's cos x plus sine x times cos x plus sine x. That's what we're doing here. Okay, so we're going to distribute this out, and we're going to be left with cos squared x plus cos x sine x plus cos x sine x. There's going to be 2 amounts of them. So 2 sine x cos x, and then plus sine squared x. Now immediately I see a cos squared x and a sine squared x, and I know a very famous trig identity that when you add those two together you must get 1. So that's all over 1 plus, and then 2 sine x cos x, that is sine of 2x from your double angles. But look at that, that's exactly the numerator that we wanted. Okay, awesome. So that is equal to the right-hand side. And therefore, we have successfully proven this trigonometric identity. Awesome. I'll see you in the next one.